Okay, in this problem we have this beam BD, and it's supported by these two rods A, B, and CD. Both A, B, and CD we're going to say have no mass. So they're massless, but they still have a force in them. They still have the force because they're supporting this beam BD. Now, have to put these dimensions in. This is my second time trying this video. So both these dimensions are 0.4 meters. So the center of mass of this beam is 0.4 meters away from this side of the beam. And we're also told that this is rotating clockwise at 6 radians per second. And right now the angle from the vertical is 30 degrees. So let's take a look at our free body diagram and identify all the forces that are acting on this beam. We know we're going to have some weight that's acting straight down, and this weight is going to be equal to mass times acceleration, which is just gravity, so mass times gravity, and this mass is going to be 981 newtons. It's going to be this 100 kilograms by 9.81 meters per second squared. Okay, fair enough. And now we have these two forces. We're going to have a force right here, this force of AB. And we're going to have this force right here, and this is going to be of CD. And now let's put in the other side of the equation, write our kinematic diagrams. And on this side, we just have to identify our masses and our accelerations. Well, let's look at what our acceleration is doing. Let's look at this point D right here. As this rotates, D is sort of moving in this circular path. So that's sort of the path D is moving in. B is also moving in this circular path. It's moving around this fixed axis right here. So that means G has to be moving in the same circular path. And what do we know about anything that's moving in a circular path? If the path isn't straight and it's moving in a circular path, or it's in curvilinear motion, it has to have both a normal component of acceleration, which points back in towards the radius of the path it's moving on. So here's our 100 times our normal acceleration, our mass times our acceleration, and it has a tangential component of acceleration. And this tangential component of acceleration is pointing in its direction of motion at that current point. So G is moving like this. So right at this point, its tangential acceleration is going in this direction. Alright, so since we're using normal and tangential accelerations, it makes the problem a little bit simpler if instead of using x and y coordinates, we use normal tangential coordinates. So this is going to be the coordinate system I use for this problem. It doesn't mean much, it just means instead of summing our forces in our x and y direction, we're going to sum our forces in our normal and tangential direction. So let's do that. Let's sum our forces in our, let's do our tangential direction. Equals mass times the acceleration in the tangential direction. Well, the only force we have in this tangential direction is going to be this weight. This weight has some component that's in the tangential direction. So if this right here we know is 30 degrees, this becomes its tangential component of weight. And this is going to be the sine of 30. So it's going to be 981 times the sine of 30 is equal to 100 times our tangential acceleration. Only one unknown, the tangential acceleration. We can solve for that, and we get an tangential acceleration of 4.9 meters per second squared, and in the tangential direction. Okay, so let's sum our forces in our normal direction. And this is equal to our mass times our acceleration in the normal direction. Well, in our normal direction, we have this FAB plus this FCD, and we also have to account for this component of weight. and it's going like this. So this is going opposite of our positive direction, so it's going to be a minus 981 times the cosine of 30 is equal to this mass, which is 100 times our normal acceleration. But we can break this down a little bit more. We know a normal acceleration is equal to our angular velocity squared times the radius, or times this r. And we have this information. We have this 6, it's moving at 6 radians per second squared, or 6 radians per second. So omega squared is 36, and r is 0.5 meters. So our normal acceleration is 18 meters per second squared. So we can sort of just substitute that in right here. And now let's go on to our moment equation. And our moment equation is going to be the sum of the moments about our center point is equal to 0. Why is it equal to 0? Well, the sum of the moments deals with rotation. Now, even though this is moving in a circular path, it's not rotating. It's the orientation of this bar BD is still the same. It's just moving in a curvilinear path, but it's not rotating. So if it was rotating, we'd have to use this moment of inertia about its midpoint times its angular acceleration. However, it doesn't have any angular acceleration. It's just purely translating. So it's equal to the sum of the moments about its center point, its center of mass is equal to 0. So let's take it moments about the center of mass. Well, look at that. Our weight goes right through the center of mass, so we don't need to account for weight. And we can break up this force right here into two separate components. We can break it up into this vertical component and into this horizontal component. So this horizontal component also goes right through our midpoint. So it doesn't have a moment. The only moment that we account for is the vertical component of the force in these bars. So we have this force of AB times, what's this? The cosine of 30 times the perpendicular distance from here to here, which is 0.4. So I'm doing it. This is my positive. So then this one's going to be negative FCD cosine of 30 times the perpendicular distance of 0.4 is equal to 0. Well, look at that. This cosine of 30 cancels out with this cosine of 30. This 0.4 cancels out with this 0.4. And we have our force in our member, or this bar AB, is equal to the force in that bar CD. That's great. So now we can substitute this force right here. So we get 2 FCD minus 981 cosine of 30 is equal to this 18 times 100. And we can solve for this force in member CD. And when we do that, we get the force of CD is equal to 1,324 newtons. And we know that CD is equal to AB, so our force in AB is equal to 1,324 newtons.